Okay, in the last class, we had started discussing the short-time Fourier transform. We had motivated the need for the short-time Fourier transform because of the fact that as you include more and more samples of a signal, and if the signal is transient, then you won't be able to tell when a frequency appears in the signal and when it disappears. Okay? So for short-time Fourier transform is nothing but basically taking your signal, windowing it, and then computing the Fourier transform of that short window. Hence the name short-time Fourier transform. Now, we had briefly talked about the trade-off between time and frequency resolution. The idea of time resolution is pretty clear from the motivation of short-time Fourier transform, which is that the longer your window is, the harder it will be for you to tell when a signal starts. So that is pretty obvious. Let's now make a formal, let's take a formal view of why having a longer window is though necessary for getting good frequency resolution. So to remind ourselves, the short-time Fourier transform definition is it's a function of two variables. This is the time samples, and these are just the frequencies, discrete frequencies, and that is equal to m from minus infinity to infinity, x of n plus m, w of m, e to the minus j lambda n. So it's just the Fourier transform of this windowed portion of your signal. Okay, we can replace, so we can say put n plus m equal to m prime, just do a simple change of variable. And if we do that, then we can equivalently write it as m prime equal to minus infinity to infinity x of m prime, w of minus n plus m prime, e to the j lambda of n minus m prime. Okay, so I'm just replacing n plus m equal to m prime, or m equal to m prime minus n. And I'll just write it in a different way so that you can relate it to something that you know well. It's x of m prime. I'm going to write it as w of minus n minus m prime, e to the j lambda of n minus m prime. Now, if you pay attention to this way of writing the short-time Fourier transform, okay, so this is your signal with just different indices, and let's look at what is happening here. If you pay attention to this, what kind of an expression are we seeing? We have summation. One signal is sort of fixed. The other signal you have n minus m prime as a function of n. What kind of operation is this? This is just a convolution operation. So if I define h of lambda n equal to w of minus n e to the j lambda n, then you can see from this expression that I can equivalently write this as m equal to minus infinity to infinity x of m prime h lambda of n minus m prime, which is simply equal to the convolution between x of n and h lambda of n. So what this means is that the short-time Fourier transform x n lambda is nothing but convolution of xn with this h lambda n function. Okay. Now, if I let's look at now the effect of this interpretation. What does this interpretation give us? So if we think about it, define the Fourier transform of this h lambda n, h lambda of e to the j omega, as the Fourier transform of h of lambda n, okay, which is equal to the Fourier transform of w of minus n e to the j lambda of n. What is the Fourier transform of this thing? So we are just taking a window and we are, what is this operation? This is the modulation operation. So you are taking a function and you are modulating it. You are taking w of minus n and you are modulating it with e to the j lambda n. Modulation in time, that means the Fourier transform of that will be what? That will be just the shift of your Fourier transform of w of minus n. Okay? So if your w of n had the Fourier transform w of e to the j omega, then this means that the Fourier transform of w of minus n e to the j lambda of n, that is simply equal to w of e to the j lambda minus omega. Okay, just follows from the basic discrete time Fourier transform property. Okay, now let's ask ourselves, so keep this in mind, that the Fourier transform of this h lambda n is nothing but this windowed function, the Fourier transform of the window function shifted to a different location. Okay. Now, I can always write, so remember the relationship between convolution and the Fourier transform. What is the relationship? Convolution in time equals multiplication in the Fourier domain. So this means that x of n convolved with h lambda of n, that is simply equal to the inverse Fourier transform of x of e to the j omega h lambda of e to the j omega. They are equivalent. If I multiply the Fourier transform of these two functions and I take the inverse Fourier transform, that should be equal to the convolution. So x of n lambda, the interpretation of that is that it's just the inverse Fourier transform of x e to the j omega h lambda e to the j omega. Okay. Now, that is equal to 1 over 2 pi minus pi to pi. So I'm just now using the inverse Fourier transform formula, x of e to the j omega, okay, w of e to the j lambda minus omega, e to the j omega n d omega. Okay. Now, fix any value of little n. If you fix any value of little n, then for that fixed value of little n, all you are saying is that I am computing x of e to the j omega n times w of e to the j lambda minus omega d omega. What is this whole operation? So let's assume that this e to the j omega n was not there. Okay, for a fixed n, this e to the j omega n is nothing but just a scalar quantity. Okay, for each value of little omega. For the time being, like, let's say that this is my entire sum function. Let's call this y of e to the j omega. Okay, for fixed n, this is not a function of n. Okay, so I have y e to the j omega, w of e to the j lambda minus omega, d omega minus pi to pi, 1 over 2 pi. What is this operation? What is happening between y and w? If this was minus infinity to infinity, and these were not periodic functions, you will call that convolution, right? So this is nothing but, this is periodic convolution. And when we did the spectral analysis using the DFT, we did this periodic convolution expression, right? We talked about what is the effect of windowing on the spectral resolution. Okay. Right now our focus is, we are interested in finding out what happens to the resolution in frequency. My n is fixed. I'm asking what happens to the resolution of my frequency in short-time Fourier transform as a function of the window. And if you recall your spectral analysis using DFT, we went through this whole process where we described that when you do windowing for spectral analysis, what happens? You get a periodic convolution of your original Fourier transform with the Fourier transform of your window. This is exactly the same expression. When you fix n, what you are getting is, you are getting periodic convolution between x of e to the j omega times e to the j omega n. What is e to the j omega n? For fixed n, that is just a phase shift. Okay, so you are computing periodic convolution of x e to the j omega times e to the j omega n with the Fourier transform of your window w. So all the things that we had talked about in spectral analysis using DFT hold here. If this W has a wide main lobe, then it's going to smear frequencies that are present in X for that fixed value of n. Okay. If this W has high high side lobes, then you are going to get leakage into other frequencies for that value of n. So all the concepts that we had learned about the windows, all ideas of windowing, which is frequency resolution, and spectral leakage, as a function of the windows, apply in this setting. In particular, if you want to, in short-time Fourier transform, if you want to distinguish between two frequencies, you better make sure that the distance between those two frequencies is greater than the width of the main lobe of your window's Fourier transform. Okay. So all those concepts apply, and in general we know what is one particular thing. If you remember your windows from the DFT spectral analysis, what is one factor that derives the width of the main lobe smaller? So two main properties of the windows that we know. One is we want the main lobe of the window to be small, and we know that the width of the main lobe is inversely proportional to the length of the window. Okay. It just follows from duality of the Fourier transform property. If you make your window shorter, it's just going to spread more into frequencies. So if you want the main lobe of the window to be small, this implies that we want the window length to be large. Okay. But that contradicts with our requirement for time resolution. Because if we make our window large, then you are now including samples from other parts of the signal where you may be transitioning from one frequency to the other frequency. Okay. So this is in contradiction to our desire for sharper time resolution. And effectively, you determine what is the right size of the window based upon what is your goal. If your goal is you really want to figure out where one frequency ends, when one component of the signal ends and the other component begins, then you want a smaller window. But the price you will end up paying is that you will lose the ability to distinguish between frequencies. Okay. So in the last class, we had talked about this example of short time Fourier transform, which consisted of a linear chirp and two frequencies. And we had given this example that for a larger window, for a window of length 401, we can distinguish between these two frequencies which are very close to each other on your right side. But there is not a very noticeable difference at where one part of the signal ends and the other part begins. On the other hand, if you reduce our window, then what is going to happen is that your main lobe is going to become larger, and because of that, your frequencies for any given value of n. So your frequencies are given by the cross sections in this direction. So these are your frequencies for any given value of n. For any one given value of n, you won't be able to tell different frequencies apart. But you can have a very good sense of when one signal ends and the other begins, because your window is now smaller. Okay. And again, what size of window to pick, that is totally a function of what kind of application you are dealing with and what is your goal. The last thing we want to talk about the short time Fourier transform is its calculation inside a digital system. So remember that just like the Fourier transform, the short time Fourier transform, even though it is discrete in n, it is continuous in the frequency parameter. So we have to, if you want to compute it inside a digital system, you're not going to be able to compute for all values of lambda. So we need to discretize the frequencies axis. And for that, we don't actually have to reinvent any theory. We can just appeal to our result about the sampling of the DTFT of a finite duration signal. So we know from early analysis that if we have a finite length signal, given a finite length signal, let's call it yn of length capital N. This finite length signal has some DTFT. Let's call it ye to the j omega. And long time ago, we had talked about the fact that if a signal is of length n, then you can compute n samples of its DTFT, and those n samples are sufficient for us to reconstruct the original signal. And what are those n samples typically? How do we compute them? They just correspond to the DFT coefficients. So n samples of ye to the j omega, in general we compute them at omega equal to 2 pi k over n, are sufficient to reconstruct xn or yn. And these n samples are simply given by the DFT expression. So we already know that fact. Now we know also that xn lambda is nothing but Fourier transform of x of n plus m w of m. So x of n lambda is just the DTFT of x of n plus m w of m, which means that we can sample this along the frequency axis. We can sample it the lambda axis as long as what is true. So a discrete sequence is uniquely determined by its samples as long as the samples are computed at intervals of 2 pi over n and the length of the signal is less than or equal to n, the usual discrete Fourier transform relationship. So if we want to now sample xn lambda in the lambda axis, forget about n for the time being because n is fixed. Okay, this thing is a function of two variables, but I'm fixing n. So I'm only talking about a Fourier transform for a fixed n. It's just a Fourier transform of a discrete sequence. And I'm saying I want to sample that Fourier transform. Okay, let's say we sample it at n points. So we can sample the lambda axis at, again, just sample them at 2 pi k over n. That is enough for me to know everything that I need to know about this sequence, provided what is true. If I want to sample it at every 2 pi over n intervals, I better make sure that this discrete sequence is what? This has to be finite duration. Okay, how can I make this sequence finite duration? Because I don't know, x could be infinite duration. How could I make it finite duration? By making sure that my window is finite duration. So this implies that W of m is of finite duration. Okay. Let's call the length of the window as W of as L. This means that W of m is equal to 0 for all m that don't belong to 0, 1 up to L minus 1. So that is the first condition if you want to make sure that we can sample the lambda axis and still recover xn plus m wm. What is the other condition that we need? We must make sure that the number of samples we collect is bigger than the length of the sequence, which is L in this case, because if my window is of length L, then xn plus m wm is of length L. So the other condition is we need n greater than or equal to L. If that happens, then I can, instead of requiring xn lambda, if this is true, then instead of requiring xn lambda, we can simply use a discrete sequence. So this notation, if you pay attention the way we have been doing, right now it's one of its arguments is continuous valued, but we can replace that by a discrete sequence x and k, which is simply given by x n 2 pi k over capital N. Okay. So just sample my frequencies at 2 pi k over n, and that is enough for me to reconstruct. Your k goes from 0, 1 up to n minus 1. So we can simply use xnk and reconstruct x of n plus m wm. Okay. In other words, we can do the short time Fourier transform calculation very fast inside a digital computer by simply using DFT, because taking the samples is equivalent to just computing the DFT. So if I want to compute this x and k, that is simply equal to n point DFT of the sequence xn plus m wm. Okay. And what will be so the plots that I have shown you earlier in figures, they are effectively just for each value of n, they effectively correspond to just DFTs for very large value of n. Okay. So if you want to now recover xn plus m wm, that is simply the inverse DFT of x and k, okay, which is simply equal to 1 over n summation k equal to 0 to n minus 1 x of nk e to the j 2 pi over n km. So 0 is less than or equal to m is less than or equal to L minus 1. And that means that xn plus m can be recovered by simply dividing by Wm. Which of course requires that Wm is not equal to 0. Otherwise you can't do that operation. So short time Fourier transform, just like the discrete time Fourier transform, can be computed explicitly by just computing samples of the discrete time Fourier transform of this windowed sequence using the DFT. And so spectrograms mostly are implemented using FFT operations because you can do them very fast. Okay. Now that is just the case for sampling the frequency axis. In some cases, you may even want to sample the time axis. So even though time is discrete time, but if you have a signal which is of length, let's say 100,000, you may not want to compute the short time Fourier transform for every little n. Okay? And the question is, can we skip some values of n and still recover the original signal? And the answer for that is true, because if you pay attention, so this thing, xnk, which is the sampled short time Fourier transform, is defined for every little n. Okay? But assume that Wm is not equal to 0 for all m equal to 0, 1, up to L minus 1. And fix n equal to n naught. Now let's ask ourselves, which samples of my short time Fourier transform do I need to reconstruct xn plus m? So if I fix n naught, I can recover x. So let's ask ourselves x of n naught. Okay. That can be recovered by simply, if I go above and plug in m equal to 0, I recover x of n naught, because that is simply given by this summation k equal to 0 to n minus 1 x of n naught k e to the j 2 pi over n km. Okay. What about x of n naught plus 1? Well, I can recover x of n naught plus 1 in two ways. One is I put m equal to 1 in this expression. In this expression, I put m equals 1. So let's say n naught was 100. I can recover the 101th sample by either putting 1 here, which means I can compute it as 1 over n w1 summation k equal to 0 to n minus 1 x of n naught k e to the j 2 pi over n km. That is one possibility. Okay. There is another possibility, of course, that I could recover x of n naught plus 1 from the same formula, this formula, by making n equal to n naught plus 1 and m equal to 0. So I could also recover x of n naught plus 1 as 1 over n w0 summation of k equal to 0 to n minus 1 x of n naught plus 1 k e to the j 2 pi k over m divided by n. So the typo is that here m is actually equal to 0 and here m is equal to 1 and here m equal to 0. Okay. Okay, but the point is that the same index, the same sample of x can be computed using two different formulas. One formula requires that I simply increase m from 0, 1, 2 up to L minus 1, whereas I fix my n equal to n naught. Okay. The other formula is that I actually increase my n naught. I increase the index corresponding to the time index of my short time Fourier transform. What this says is that I could, for example, have thrown away x of n naught plus 1, the whole values associated with the index n naught plus 1, and still have recovered everything about my sequence. Okay, because I could recover x of n naught plus 1 by simply increasing or incrementing my little m rather than incrementing little n. So the general principle is that x of n naught and k for so we can recover x little x of n for all n between n naught and n naught plus L minus 1 using capital X of n naught k only. Okay. So rather than going to x of n naught plus 1, x of n naught plus 2, x of n naught plus 3, and so forth, I could simply recover all values of my samples between this range by actually incrementing little m in that formula. Okay. Which means that I could actually throw away, we can throw away x of n naught plus 1 k, x of n naught plus 2k up to x of n naught plus L minus 1k, and still not lose any information about x of n. Okay. So short time Fourier transform has just like discrete time Fourier transform has enough redundancy for finite duration sequences that you can only sample it in some locations and still know everything that there is to know about the sequence. Short time Fourier transform has also redundancy in the time domain. If your window is of length L, and the key thing is that every sample of my window has to be non-zero. Okay? Otherwise, I cannot use this division by WM. If every sample of my window is non-zero and my window is length L, actually my short time Fourier transform has a lot of redundancy even in the time domain. I can throw away samples associated with different values of n and still recover my original signal sequence. Okay. So in general, you can subsample we can subsample the short time Fourier transform in both n and lambda axes. So we can subsample it and recover xn from the subsampled short time Fourier transform. The subsampled short time Fourier transform can be written as x r capital R times k, which is equal to x of r capital R 2 pi k over n. So what this means is that and r equal to minus infinity to infinity and k equals 0, 1 up to n minus 1. Okay. What this is saying is that you can, in the time direction, in the time indices, you can throw away every n minus 1, all n minus 1 samples, just keep the nth sample, rth sample. So you can throw away all r minus 1 samples of your short time Fourier transform, just keep the rth sample. And in the frequency axis, you can throw away all values except n samples and still recover xn. But what this requires is a few conditions. The number one condition is that your window has to be finite duration. Otherwise, you cannot do sampling in the frequency axis. So our window has to be and we call it capital L. Okay. The other assumption is that the number of samples that we take in the frequency domain have to be more than the length of the sequence, which is the length of the window. So our n has to satisfy that it is greater than or equal to L. And the third is that we are going to keep every rth sample in the time duration. But for that to hold, I must stay within this range that we had talked about. Okay, I can recover up to L samples. So my R better be smaller than capital L. Okay. So the third condition is that our R has to be less than or equal to L. And the fourth condition is that if you want to do sampling in time, then your Wm must be non-zero for every value of m, where it is between 0 and L minus 1. So Wm cannot be 0 for all m equal to 0, 1 up to L minus 1. If you satisfy these four conditions, then short time Fourier transform can be subsampled in both the time domain and the frequency domain. So here is a visualization of what we are talking about. Again, short time Fourier transform is discrete in your time index and continuous in your frequency index. So this is the real short time Fourier transform, x of n lambda And we are, so each of these lines are continuous. They are basically, these lines correspond to the discrete time Fourier transform of a windowed portion of your signal or sequence. Okay, and this is the true thing. Now, what we are talking about is that we can sample this further. We can sample it so that it can be appropriately stored inside a digital system. So one part is we can sample, for each value of n, we can sample the frequency axis. So we can sample the frequency axis from 0 to 2 pi by talking about 2 pi over n. So just store this value, okay, which is 2 pi over n. Store another value, which is at 2 pi times 2 over n. Store this 0 at the 0 frequency, and so forth. Okay, so you create n samples in this direction, n frequency samples for each value of n. But you can also not only samples in the frequency domain, you can also throw away the short time Fourier transform for certain values of little n and still have all the information. So in this case, n equals to 10, which is the number of samples you are going to collect in the frequency domain. And r equals to 3, which means that you are going to keep every rth time sequence and throw away the other r minus 1 sequences. So you will have this discretization of the frequency axis, and then you will throw 1, 2, keep 3, throw 4, 5, keep 6, throw 7, 8, keep 9, and so forth. So this is a subsampled short time Fourier transform x of r, r, k, okay, whereas you see you have just sampled the frequency axis every 2 pi over n interval, and you have thrown away this line. So these values are thrown away in between. Okay. And this smaller version of the short time Fourier transform is enough for you to reconstruct the original sequence. Now, of course, if you are visualizing it, right, you will lose some information in your visualization, and that depends upon how much you are willing to subsample in the time domain. Okay. Similarly, in the frequency domain, just like we talked about, you want to use enough samples so that you get a better sense of what the frequency spectrum looks like. You don't want to use too large of a capital N because that will take a large computational time. But you don't want to use too small of a capital N because then you can't get a good sense of what the underlying Fourier transform looks like. Okay. So in general, though, this is what you want to do is satisfy this constraint. R is less than or equal to L is less than or equal to N, where L is the length of the window. And of course, once you pick the window, you have to decide all the other things that we have talked about, window selection. And we have done rectangular window, Hamming window, Blackman window, Kaiser window. All those things play a role to tell you how your resolution in frequency will be affected. So if you use MATLAB spectrogram function, you can tell it which window to use for computing the sampled short time Fourier transform. Okay, our focus in the next 5 or 6 lectures will be talking about some other properties of orthogonal transforms. In general, we'll like to spend a little bit more time discussing about the wavelet transform and why it's important in the modern processing realm. But the first thing that we need to learn about is what is sort of a good transform in general. for certain kinds of processing needs. Okay. And one of the most important properties of any orthogonal or orthonormal transform is what is known as its compressibility or its energy compaction. So we'll try to formalize what these terms mean. We'll start off with a very simple transform, which is the discrete cosine transform. We'll look at why that is better than the discrete Fourier transform in terms of energy compaction. And from that, we'll then move on to discussion about how do you build the wavelet transforms, what is the relationship of those in terms of frequencies and so forth. So to talk about this, we have to go back to the abstract notion of the orthogonal transform that we had studied earlier. I'll be switching between the matrix vector notation of transforms and the sequence notation of transforms. If you get confused, please do let me know. So remember, the definition of orthogonal transform is that you are given a vector Rn, where Rn, R capital N, where we construct the vector by putting the samples x0, x1 up to x of n minus 1. An orthogonal transform is characterized by an n by n matrix which we typically write as U, okay? And it's orthogonal because the different columns of your matrix are orthogonal to each other. You can either think of it that way, or you can say that the columns of the matrix correspond to discrete time sequences, and they are orthogonal to each other. Right? It's the same thing. So orthogonality in linear algebra, for example, is that if you are given two vectors A and B, if they are complex valued, then orthogonality is defined as A Hermitian B equals to 0. If they are real valued, then it's defined as A transpose B equal to 0. Okay. If you think of each vector as just samples or a discrete time sequence, okay. For example, you could think of one A being equal to A0 up to an minus 1, and B equal to B0 up to Bn minus 1. And if you write this orthogonality expression, then that is simply equal to saying that n equal to 0 to n minus 1, A of n Hermitian A and conjugate Bn equal to 0. Okay? So it's just a generalization of the orthogonality definition that you have seen many times before about orthogonality of your of the discrete sinusoids and so forth. Okay? So an orthogonal transform is one where the columns of U are orthogonal. And we had talked about, for example, one of the orthogonal transforms we had talked about was the special case where U Hermitian U equals to alpha times identity. Okay? And an orthonormal transform, we had talked about the case when alpha equals 1. So an orthogonal transform is U Hermitian U equal to alpha identity equal to alpha U Hermitian. That is sort of one. It's not the only way to write an orthogonal transform, but that is one of the ways. If alpha equal to 1, the orthonormal transform is always given this way. So you have a problem given in the assignment, but I'll effectively prove that here too, which is that all orthogonal transforms given by U Hermitian U equals to alpha U Hermitian equal to alpha times identity have a Parseval's relationship. So we have seen that many times in the DFT case, but that Parseval's theorem or the Parseval's identity is actually more general than just Fourier transform. It's actually a property of any orthogonal transform. Okay? And the relationship is that if you look at the energy of your sequence in the time domain, n equal to 0 to n minus 1, that is equal to 1 over alpha times the energy in the transform domain, n minus 1 x hat of k absolute squared, where x hat of k I am defining as are the transform coefficients of x. In other words, if I define a vector x hat, okay, that is equal to x hat 0, x hat 1, up to x hat of n minus 1, and that is equal to simply u times x. Okay. So we had talked about it earlier too for the case of the discrete Fourier transform, right? This u for the discrete Fourier transform is nothing but a Vandermonde matrix, and these x hat are the DFT coefficients. But right now we are talking about in a very abstract sense. If you are given any orthogonal transform which has this property U Hermitian U equal to alpha identity equals to U Hermitian alpha times U Hermitian, effectively any orthogonal transform. It could be discrete Fourier transform, discrete cosine transform, the discrete wavelet transform, which are orthogonal, the orthogonal versions of them. It could be the Hadamard transform or any other transform. If it is an orthogonal transform, that it is going to have this Parseval's identity. And what is this identity saying? That if you look at energy, this summation and absolute value squared, this is just a way of saying what is the energy in your sequence. The energy in time domain equals some constant times the energy in the transform domain. Okay. For orthonormal transforms for which alpha equal to 1, this is exact equality. Energy in one domain equals energy in the other domain. Okay. So energy effectively is preserved under orthogonal transforms. You can think of it as energy preservation. To Parseval's identity is effectively talking about energy preservation. Okay. Now, energy compaction. So we know that if I look at all of my n transform coefficients, if I look at, for example, all of my DFT coefficients, the energy in all those DFT coefficients has to be equal times the scalar factor. So remember the way we have defined DFT, alpha equals to n in our setting, okay? Because our DFT is not orthonormal, it's orthogonal. So it is true that if I sum all of if I look at the energy in all of my DFT coefficients, that is equal to the energy in my signal. But what energy compaction says is that good transforms actually have most of the energy concentrated on a few coefficients. So energy compaction means that most energy in the transform domain is concentrated in a few coefficients of x hat. Okay. So an example will be, let's say I plot x hat k absolute value. Okay. And again, I want to say that this x hat could be any transform. Doesn't have to be DFT. And let's say I look at the transform and it looks like this. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So this, when I look at this transform, what do I see? I see that most of the energy is concentrated in 5 coefficients. All the other coefficients are 0. Now this is an extreme case. It could be that the other coefficients are very small. But effectively what this is saying is that if I look at the energy in the entire transform domain, x hat of k square, okay, that is approximately equal to, in this case it is exactly equal to x hat 0 square plus up to x hat 3 squared plus x hat 10 squared. Okay. Although the total number of coefficients, the total transform domain is 12 dimensional, capital N equals to 12, we need only 5 coefficients to describe the signal. Now why is energy compaction important? Because at some level what it is saying is you need to store inside a computer only 5 coefficients rather than 12 coefficients in this case. And storing less coefficients means you get to compress your data. That is effectively what, for example, JPEG is doing. The way JPEG works is you look at this huge image and you don't shrink the size of that image, but you run it through, lower the quality a little bit, and you can't really tell that there is a much difference in the quality, but the size of the image gets reduced sometimes by like 10 times. Okay. That is the principle that is at work in that kind of thing. So energy compaction is a very important property when it comes to, for example, compression. It is also very important in terms of things like denoising. If your signal has noise, since we are not doing statistical part of signal processing, we can't go into that detail. But in general, we are always interested in orthogonal transforms which have compressibility or compaction property. And in the next class, we'll describe this property a little bit more formally and then look at the discrete cosine transform, which tends to have better energy compaction than discrete Fourier transform. Okay?